Hello everyone. Right, so although the title might seem quite complicated, I assure you that my talk is going to be fairly benign. I would like to divide my talk into two halves. First, I would talk mainly about the motivation and the reason why the problem is important to us. And then second, I would talk about some results and the techniques. Right, so as many of you might be familiar with, the problem of influential detection is nothing but finding the nodes which are highly influential in a network so that you can maximize the spread of the influence or a spread of a desired information in the network. For example, the figure on the left shows Times Magazine issue of the 100 most influential people in the world. So what this, when we say about influentials, we generally think about people like celebrities or popular figures. So what these people can do is when they endorse certain products, they tend to spread the reach of the product to a larger audience, and that results in higher product adoptions. But generally, this is not true because when you see how we buy products, it's generally from an influence through a friend or a friend of friend, rather than because a celebrity endorses a product. Although I have some of my friends who buy products just because a celebrity of their a known celebrity endorses the product, but the figure on the right shows a random guy who claims to be a real influential. But what this says is that any person can be an influential in a network depending on the type of information that you want to spread or the type of the network, and that really is more important here rather than just saying that an influential is just because he is a celebrity or a popular figure. So like many of you might be familiar with the applications of this problem is in various fields. For example, of course, in viral marketing, where you would want to identify a set of individuals to offer freebies so that when they spread their influence, you would want to result in maximum product adoptions. Or in water distribution networks, which some of you might not be familiar, where you want to detect contaminants at a much earlier stage. So you would place sensors at certain locations in the network, which would maximize the spread of the contaminants and hence help detect the contaminants earlier. And of course, in preventing the spread of diseases, where people have these models of epidemiology and so on to identify people or patients to vaccinate or provide treatment with priority, and hence to contain the spread of the epidemic or disease. This problem of influential detection it's shown to be a NP-hard problem to obtain an optimal solution, but there are several heuristics and algorithms. The simple heuristic is this: just to take the node with the highest degree as the most influential, which is just a simple heuristic but doesn't provide the optimal solution. So our problem is a subtle variation to the actual influential detection problem, where instead of focusing on the entire network to spread your influence, we try to focus on a subset of nodes in the network to spread the influence. Although this is just a subtle variation, it has several applications based on the choice of subset that you can take. For example, a grocery shop or a small business might want to target users within a 2-mile radius of its shop, or in a political campaign where the parties might want to propagate the campaign through supporters or fans and critics. And of course, the natural segregation is to use the demographics, which is either nationality or age or the gender. Another one I was thinking about was when one of the talks in the industry panel that the eBay, when the products was sold in the first auction, could be to even segregate based on the choice of the users, where you can, based on the interest of users, you could segregate the subset. But the real thing is, even if you choose a subset based on whatever category, the problem of detecting influential is independent of this choice of subset. So we could model any such subset and then use the underlying network to frame the problem to do this subset-specific influential detection, where our primary motivation has been that nowadays the size of networks, especially online social networks and so on, have increased in size and density tremendously, that this gives us more opportunity to target this problem as a standalone, which helps us improve the efficiency over traditional approaches. since the current state of the art, although talks about this problem as a subtle variation to the influential detection problem, it doesn't it just use the existing algorithms to be adapted to the subset specific version, which I would talk about the adapted versions as well. Like in the general case, even in this subset specific version, you could just use the simple heuristic where you find the node with the highest relevant degree instead of the highest degree. Right. So our contribution in this paper is here is a brief summary where we first design an efficient algorithm for the subset specific problem, and then we provide a tunable parameter which is nothing but the susceptibility of a node to design the efficiency, to trade off between the efficiency and performance of the algorithm. And then since traditional approaches use a static graph where the graph doesn't change over iterations, we provide an analytical framework to analyze the influence spread function when the graph is iteratively pruned. And we also show that the influence spread function remains to be submodular when the graph is iteratively pruned, which helps us offer performance guarantees. So this is just, like I said in the first slide, the type of the influential depends on the network type and the network type of information. So all these are the dynamics of information diffusion, which you can capture in the form of model. For example, as a most popular model is the independent cascade model, where a node's influence or a node activates its neighbor with a probability p. Since this is a stochastic model, you could see the activation of a node u by a node v as just as a coin flip outcome of a coin flip, which has a bias p. And what this helps us to do is that since all such activations are independent of each other, you could generate what is called as an activation graph. And when several such activation graphs are generated, you could compute the influence spread. Actually, the problem here is that since it's a stochastic model, so you would want to compute the influence spread in a deterministic way or through simulations, which you can do using this. So this is just a technique which shows how you could use these different activation graphs to compute the influence spread in expectation, just to by using the mean number of nodes reachable in the graph. So I'll just skip this. So one of the famous or the more popular algorithms here in this influential detection problem is this greedy algorithm, where you choose a node with the highest marginal contribution as the most influential node. For example, suppose nodes v and ua are sorted in the order of their marginal contribution. First, when you choose v, then the marginal contribution of u, even though it was higher in the first iteration, it reduces in the second iteration. So ultimately, what you want to do is you want to maximize the influence spread due to all the nodes in your influence set. So you choose A. So before I go to our approach, I'd like to state our problem statement more formally. So which is given a graph and what we call a destination set, which is the set of nodes that you want to maximize the influence. So the goal is to find top k nodes which maximize the spread of influence to this destination set. And one interesting feature is that your set of influentials actually may or may not lie in your destination set itself. For example, in the first figure, based on the destination set as highlighted in green here, the node A could be the most influential, whereas in the second figure, your influential actually lies in the destination set, which is node B. Also, when you choose the entire set of nodes in the graph as the destination set, your problem reduces to the standard form. Hence, our approach can also be used to the standard problem of influential detection. This is just a naive extension to the greedy, which we call it the subset adapted greedy, where instead of, like I showed in the previous couple of slides ago, that you can compute the influence spread in the network. Here, instead of computing the entire influence spread in the network, we just find the number of nodes which are reachable to the destination set and then compute the node which has the highest influence spread as the most influential. So this our approach, we call it the iterative pruning algorithm for influential detection, which is first to identify a set of nodes which are considered influenced, and then to deprioritize the spread of influence to all nodes in the set of influenced nodes. We do this by computing the likelihood that a node would be influenced due to a seed set, which is the set of influentials. This is nothing but the expectation that a node would be active due to a seed set A. This gives us final resolution to analyze the influence spread using the equation above. Also, then we set a threshold which is called the susceptibility or the ease of influencing a node, which we call it gamma. And when LU greater than gamma, you could assume that the node is considered influenced. Unlike other threshold parameters, like some of you might have come across the linear threshold model and so on, where it incorporates the influence only to 1 hop or 2 hop neighbors. This parameter actually incorporates the influence from all over the network. Hence, we see this as a more efficient way to compute the susceptibility of a node. This figure shows, this is the step after we find the most influential node. We then find the nodes which are considered influenced, as highlighted in blue. And then the next step, which is the final step, is to prune the network, which is what gives us the most efficiency gains. We do this by removing all paths that lead only to nodes in the influence set. For example, it's basically a two-level process where first the nodes, adjacent nodes are removed, and then recursively we remove all the paths to the uninfluenced nodes. But the key thing here is that this process, when done iteratively, gives very significant efficiency gains. We have shown it both analytically and through experiments, where we choose 2 academic real-world co-authorship networks as our data set, and we compare our algorithms with the subset adapted versions of greedy and self. Self is just another technique which builds on the greedy to propose an efficient technique for influence maximization. And then we analyze our system parameter with different values of gamma, which is based on the as a function of the propagation probability. The reason for this is that when you see in a network, the likelihood that a node gets influenced depends on the number of paths and the number of hops it's from the influence set. Or you can say when the set of influentials are 2 hops away, you could say that the node's influence is not, likelihood that the influence is not as high as compared to when the influential is about 1 hop away. So this is the primary motivation to choose the gamma as a function of propagation probability. So our experiments show up to 96% improvement in the efficiency when compared to greedy, and about 52% improvement in efficiency when compared to self. Whereas with a 10% drop in the influence spread, like I said, the choice of gamma determines the tunable parameter which you can use to trade off between the efficiency gain that you get and the drop in the performance that you get. While in this case, you get a drop of about 10% with a gain in efficiency of about 96%. And another data set, which is a sparse network that we chose, we had an efficiency gain of about 73%, with a much higher drop in influence spread. So what we can infer from these is that when you choose low values of gamma, they are generally highly efficient, but it comes at a cost of performance loss, which is okay. But when you have a desirable performance, you have to make an informed choice of the system parameter. So one good choice is that when you have a denser network, you can of course choose a low value of gamma to get a higher efficiency with a desirable influence spread. Whereas when you have a sparse network, you would like to use a higher value of gamma or a higher value of susceptibility for the nodes. Right. So since the network is pruned iteratively, what we found is that the influence spread function may or may not be submodular, which is very important for this problem, because submodularity guarantees performance. Submodule can be used to evaluate performance guarantees. But as it was shown in a previous work, where in a static graph the influence spread function can be submodular. But the real question is, when you have a pruned graph, when you have a graph which is iteratively pruned, does the function still remain submodular? Well, we do have the answer, but for details you could refer a paper here. And another important question is to estimate the influence spread, which is on the original graph when the graph is iteratively pruned. Since the pruning itself is done only to improve the efficiency, we do this. We need to compute the actual influence spread on the original graph. So we do this we derive a lower bound which helps us evaluate this influence spread. And finally, to summarize our work, basically we propose an efficient algorithm which is especially targeted for the subset specific problem, and still it can be used for the influential detection problem. as a general. And our experiments show significant efficiency gains with the data sets that we use, and the analytical framework helps us show that this influence spread function still remains to be submodular, which can be used to evaluate performance guarantees later. And we can also use the tunable parameter to trade off between the efficiency and performance that you want. So the scope of one real interesting scope of future work is that, as you can see, nowadays people are beginning to calculate the susceptibility of nodes on Facebook and so on. For example, in one of the keynotes yesterday, we were told that nodes who are on Facebook, people who are single or based on the relationship status, you could find whether nodes are susceptible or not. For example, people who are married were found to be the most susceptible. So when you have such real-world distributions of susceptibility, you could use it to evaluate the algorithms better, and this will definitely work better on when you have real-world data. These are just some of the. Any questions, please? Thank you.